Okay, so we're going to start by looking at aryl halides and how we can get them to be reactive. Because aryl halides are attached to an alkene, they aren't typically reactive in normal conditions. Oh, that's unfortunate. Okay, I fixed it. So, sorry about that. So, to make aryl halides reactive, an important thing that we can do is add electron withdrawing groups. So in this case, I added NO2 at the ortho and para positions. Now, this will not work at the meta positions because if you draw out the resonance structures, the negative charge from removing the fluorine, or the positive charge, sorry, will never end up in a spot that can be stabilized by the nitrogen and oxygen. So I'm not going to draw out the resonance, but I will draw out a sort of reaction. So we'll go ahead and say that, I'll ignore that that's curved, that this reacts with Na plus and OCH3 minus. So, like I said, under normal circumstances, without these electron withdrawing groups, this would not be reactive. But since we have them, and you can even add heat to make this reaction proceed even faster, but we would have substitution at the, oh, I didn't draw a bond, at this position where the fluorine was, and we will have the addition of OCH3. And I'm not going to draw in the nitrogens, that just takes too much time. Anywho, so that is one of our reactions that we can do with these aryl halides. Another one would be so another type of reaction we can do to make these aryl halides useful in a sort of laboratory sense is, for this one, you don't necessarily need the electron withdrawing groups, you just need this specific reactant. I don't know why these arrows are curved, just ignore it. You need this specific reactant, which is NaNH2 and also NH3. Now, the thing we're going to be adding is actually this NH3 because we're going to, we're going to be adding NH2. And this reaction proceeds by removing a hydrogen, a beta hydrogen, next to the aryl halide. So here's our hydrogen that we will be removing, and you don't have, so this doesn't have to be the hydrogen you would remove. You could also remove this hydrogen, which obviously makes the stereochemistry of this product variable. So you would get a mix of products, say if you had a carbon or a methyl group right here. So for this case, we'll just go with this. And this reaction would proceed by making a carboanion, which would then kick off this fluoride and make an alkyne. So the alkyne in this case would become right here between the hydrogen and the fluoride. Why am I saying fluoride? I really mean fluorine. Anyways, so this anion is stabilized by the alkyne, and the alkyne is when the NH2 can actually attack it and add into the ring. And the anion is still going to be in the ring after after the addition of NH2. So I'm going to draw this intermediate. So the NH2, put it here. That, I did not type that. Okay, I drew a intermediate for this reaction. This is supposed to be a lone pair and a negative symbol. And then this would obviously pick up a hydrogen from the NH3 in solution. And this anion, the electrons would go to the hydrogen, and this whole system would be complete. So yeah, those are two ways to do aryl halide substitution, I guess. And we're going to get into how to form new carbon-carbon bonds with aryl halides. So because a lot of these reactions, like I said, aren't favorable to take place under normal conditions, a lot of them use transition metals to catalyze the reaction. So I'm going to go ahead and draw something up quick. Okay, so this reaction is the Nagishiki coupling reaction. So this one is really characterized by the zinc, and the zinc is usually next to a halide. In this case, it's Br, and the zinc carbon bond is really the important factor in this compound. And then we have our aryl halide. I used Cl in this scenario. So for the reactants, palladium is going to be a very important catalyst for this reaction. It wouldn't have gone without the palladium catalyst. And we'll have THF as our solvent. So this reaction makes a new carbon-carbon bond, and you could probably guess where it will be based on the lack of complexity in these compounds. This carbon here is going to drop this bond with zinc, and it's going to create a new bond when this halide leaves with this carbon. So I'm not going to go through the mechanism of that, but we're just going to connect these two compounds. I should have waited to draw that bond, I guess. So we have this, and this is going to connect. It won't reach. There we go. Well, that's not very pretty, but you get it. Now, this is going to get pretty repetitive, so I'm going to just edit what I have here already. Oh my goodness, that's not what I wanted. I'm just going to edit what I already have here. So for the next reaction, we're just going to change this to be ten but3. So again, use of a metal, and the same thing will end up happening. We use palladium 0. This solvent would actually probably work better as toluene. But yeah, the same general scheme would happen. This carbon and this carbon would form a bond, and it would create this structure here. So the next one we're going to be looking at is Suzuki, and Suzuki is a little different because the molecule is a bit more complex. It's going to be using boron, a boron carbon bond, and sometimes you have to make these in the lab. So you have to make either a boronic ester, an organoborane, or a boronic acid. So I'm going to go ahead and draw boronic acid really quickly. So here we have the Suzuki reaction, and here's our boronic acid group right here. And this would be prepared by taking an organolithium and reacting it with a boron oxygen compound. and that would give you a boronic ester, and then you can react that with water and get the boronic acid. So basically that's where we're at. We got to here, and now we're going to take our reactant and react it with our compound, our aryl halide. So this is going to do, once again, the exact same thing. This boron is going to get kicked out, this carbon and this carbon are going to form a bond, and the Cl will also be kicked out. And obviously the solvent is a little bit different. In this case, you would probably not use toluene, you'd probably use THF, water. I have K2CO3 and 4ppH3. So each of these reactions is a little bit different in their actual mechanism and solvents and obviously physical properties and such, but they all do the same thing. So Suzuki reactions are actually kind of cool because if you have a boron, like if you have two boron groups on this, if I had another one up here, this would react to make this, and then we'd have another boron group, and it would keep reacting and keep reacting and keep reacting until we have this long polymer, and that only stops when we run out of one of our reactants. So that's kind of cool that the Suzuki reaction can do that. So our last one is the Sato-Gashiro reaction, and in this case we're going to be using copper iodide to fuel the reaction. So let me draw this up. Alright, so this reaction uses an alkyne. Oh, that is an alkene. It's supposed to be an alkyne though, just pretend it's an alkyne. And like I said, we'll be using, that is not, okay, whatever. Copper iodide, oh my goodness. And, oh yeah, we would have palladium 0 in there still. So, but once again, same thing. It does the same thing. Yep. So there is one type of reaction that can occur without a metal catalyst, or no, not a catalyst, sorry, without a transmetallation step, and that would be the Heck reaction. So the Heck reaction, we have our aryl halide, and we will have an olefin, which is a alkene. I'll just draw some basic. Oh, that's not connected. Okay. That just nothing works on this chem draw, does it? Alright, there's our alkene. And you can have some other stuff on there. You can have an oxygen here. Sure. Whatever. So, let's say this is our compound. And we can react it to make with palladium as our catalyst. Palladium 0. And okay, so this reaction, there's a lot of steps. Yeah. So this will create another CC coupling, and the CC coupling will occur at one of these positions by the alkene. So we're going to have our, say our alkene, oh that is not where my halide was it? Our halide is going to get replaced to a bond to this alkene, which is bonded to that O, which is bonded to a carbon, and another carbon. Okay. So this would be our compound.